Alright, so here's an intro to a robust control system. Generally in systems, an input is received, passed through this system, and the output is produced. An example of this would be a DC motor, where the input would be a voltage or a current, and the output is the angular speed of the rotor. Another example would be a heating system with a desired temperature and an actual current temperature. In both of these systems, we wish to control the output precisely. This is done through a control system with feedback. The feedback gives us measurements of the actual output and allows us to control it with adjustments. Controllers are used to correct the error between the desired output and actual output, and also to quicken the response time and lower the overshoot of the system. For example, in a heating system where the desired temperature is supplied, the actual temperature is fed back and used to adjust the temperature. The time it takes to settle to the desired value is called the settling time. And the value, the max value above the desired value before the settling time is called the overshoot. To make the system robust, a pre-filter is used to block out frequencies that are difficult for the system to deal with.
Before we dive in the actual implementation of the system, let's analyze the importance of a PID controller. First, what is a P controller? Well, let's say we are working with a heating system. The room temperature is 22 degrees and we want to increase it to 28. Without a P controller, the system will take hours to set the room temperature to the surroundings of 28. To accelerate the process, we add a P controller. With a P controller, the system will take minutes rather than hours to change the room temperature from 22 to the surroundings of 28. However, we do not want to reach the surroundings of 28. We want to have a temperature of exactly 28 degrees. Hence, we add an integrator to have a steady state response of exactly 28. Yet, the integrator is not flawless as it introduces an overshoot. Hence, the temperature will attempt jumping to 35 before stabilizing to 28. We fix that by adding a D component. Merging all controls together, we get the optimal response of the system. We use a P controller to accelerate the response of the system, an I controller to get the exact response during steady state, and the D controller to remove the overshoot. Now, let's get into the implementation.
Now that we understand what the PID controller is for and what it does in a control system, we can move on to realizing the whole robust control system. The first part of the robust control system is the pre-filter. The pre-filter circuit is shown below. The next part of the system is a differential amplifier, which takes an input from the pre-filter output and also from the feedback. The next part is the controller, the summer, and the inverter. In this case, we have a PID controller. We need a summer and an inverter. The summer circuit just gets the outputs from the PID circuits and adds them. The output from the PID circuit is inverted, therefore we need to invert once again. Next is the plant, which includes the driver, the motor, and the tachometer. The driver increments the current from the controller in order to drive the motor, and the tachometer turns the angular speed of the rotor to an electrical signal. Next, we can see the full completed realization of the robust system.